class on statistical mechanics. This is a TA course that I'm doing as part of my PMRF tuition. I'm Sarvi. I'm a PhD student here at IISER. And in this course, we have been discussing about statistical mechanics. We started with thermodynamics, then we talked about, the very concept of probability and the probabilistic approach that leads to statistical mechanics. And there we discussed about the different ensembles, okay, and tried to relate the microscopic picture with the macroscopic picture. Then we moved ahead with the matrix formulation, which helped us, or which made it easier for us to deal with quantum systems. So that's how we actually went towards quantum statistics, where we saw that based on whatever particle you are talking about, based on the nature of the particle, or based on whether your particle is defined by a symmetric wave function or an anti-symmetric wave function, based on all that, your, how you distribute these particles into different energy states differ. And that again affects the thermodynamic variables or the macroscopic variables. Okay. So we tried to relate the two, and we did find expressions for mean occupation number, what's the relation between the grand canonical partition function and the fugacity and this number distribution and all of that. And from there, we tried to get expressions for pressure, average energy, number of particles, and all that. Okay. And we did that for fermions. We did that for bosons. So in the last class, we have been talking about ideal post gas, and we try to see how one can define the mean occupation number, and then from there relate or try to write the Q potential in terms of the number distribution, and from there try to define the thermodynamic variables. We saw that there's this phenomena of Bose-Einstein condensation that happens below a certain temperature called the critical temperature. And that again depends on the number density that can depend on, that can have a typical relation with the number density based on what is the dimension of our system, what is the energy dispersion relation. Okay, so based on all that, the expressions or the very phenomena of Bose-Einstein condensation can depend on all these factors. And then one can define. So if Bose-Einstein condensation happens, then you get a well-defined critical temperature, and otherwise you might not get it. So we also discussed cases where condensation can happen and where it is not expected to happen. Okay, so today we'll follow up with it, and we would go ahead, with this bosons, but then talking about different systems. Okay, not just free particles in three dimension, but also other kinds of systems where there are potentials and how the the energies are different defined, and based on that, how do you use the same technique, but how do you generalize it even further. Okay, so that's about today's class. So we'll discuss the basic concepts and the formula. We'll try to solve certain questions. Many a times, whatever the concepts that we are discussing, or the general formulation that we'll be talking about, will generally there are questions that directly make use of these concepts. Okay, in different competitive exams or even in the assignment questions and so on. So understanding this concept is very important. We'll also solve some questions, and if there are any doubts, feel free to reach out. Okay. So a quick recap. So we talked about ideal Bose gas, and there we saw that, so if you have to define, this is your Q potential, okay, and you can write it in terms of the grand canonical partition function, capital Q, and this is the relation. And you can see that this is how it's related to the fugacity and the energy distributions, right? So here, because it's a Bose gas, you have a minus sign here. If you have a fermion, these expressions would slightly vary. So the general expression is written in terms of A, right? Where A is 1 for fermion, A is -1 for bosons, and A is 0 for a classical particle. So we also saw that if you have to write an expression for the average number of particles, this is how you would write it. So here, this term here is called the mean occupation number. Okay, so it gives you a measure of the average number of particles in different energy states given as epsilon. Okay, and from here we would see that for this to be defined, this term here should be a non-negative quantity, which gives us a range of values for Z, or gives us a relation between the chemical potential and the available energy states. Okay. So for this to be a non-zero quantity, what we need is Z e to the power minus beta E should be less than 1. And Z is nothing but fugacity, which is given as e to the power mu by kT, right? So now if you put in here the expression of Z, you would get a relation between mu, the chemical potential, and the energy. And it tells us that mu should be less than epsilon, which implies that chemical potential must be lower than the ground state energy. Okay, so now if you're talking about free particles, the lowest energy can be 0. So in that case, your chemical potential should be lower than 0. Okay, and from here you can actually set a limit to the typical values of Z, which lies between 0 to 1. Okay, and we would see that if you remember, we would also discuss now that as we go, like when condensation happens, or as we go below the critical temperature, Z tends towards 1. Z becomes 1. Okay, at higher temperatures, it is low. Now, if you consider a large volume where the spectrum of single particle states are continuous, then you can actually move from summation to integration. Okay, and this is how the integration would look like. So here it's written in the general most term based on whether it's fermion, boson, or classical particle. You can put the value of A accordingly. And here when you do, so now you're going from the summation to an integration, which goes from 0 to infinity. So you can see you're doing an integration over the phase space volume. You can also rewrite it, we would not go into the details because this is something we have also discussed in the last class. But the main point is you can rewrite it in terms of energy as well and get an expression for the density of states for in terms of energy. And here, if you rearrange these terms to try to do this integration, you'd get a term like this, which tells us that the expression for pressure depends on this derivative that you can see. So it depends on the functional form of energy on momentum, right? So for a free particle, we know that energy is given as p squared by 2m. For some other, relativistic particle or something, we know energy is given as p into c. So based on what is the dispersion relation that relates momentum with the energy would play a role in defining the expression for your pressure. Okay. And for Bose gas, we put A equal to -1. Now, for non-relativistic free particle, energy is given as p squared by 2m. So from there, if we want to go from, so you had 4 pi p squared dp, right? In the integration, you have here 4 pi p squared dp, but you can also then write this in terms of energy, right? By using the relation that energy is equal to p squared by 2m. So you can do the substitution. So basically now you get a density of states, which gives us a measure of how many states are there between energy epsilon to epsilon plus d epsilon, right? And this is how it goes. So here you can see that the density of state for a three-dimensional free particle goes as epsilon to the power half. Now, obviously, if it is a two-dimensional system or a one-dimensional system, this density of states would vary. Why? Because then the integration over the phase space volume that we just did would change, right? So that means based on whatever dimensions we're talking about, your density of states expression would change. So for 3-dimension, it goes as epsilon to the power half for a free relativistic particle. But now if you go to 2-dimension, you see that it becomes independent of epsilon, while in one dimension, it becomes epsilon to the power -1. So based on what dimension of system you are dealing with, your expression for density of states would vary. Now here, one important point to note was that if you look at the expression for density of states, here it assigns a 0 weightage to 0 energy, which is not really true, because especially for the Bose gas, we know that there's no limit to how many particles can be contained within a single state. So that means you can actually have all the particles coming and getting accumulated to the zero energy state, which is actually not considered in any way here. Because here, if you put epsilon going to zero, your density of state goes to zero, which means that there's nothing in the zero state, which is not true, right? So in that case, we have to actually explicitly introduce the epsilon equal to zero term. Okay. So if you do that, this is how it would look like. So this is your term for the epsilon not equal to zero term, but for anything but for epsilon equal to zero, you have to explicitly write the expression. Okay. Similarly, for the number of particles, you can do the same. So what you are basically doing is in this expression, suppose this is your expression here, if you put epsilon going to zero, right? So that would give you this term that you just saw, right? So you have to explicitly consider the case where for the zero energy level. Okay. And now you actually have an expression for pressure or the number of particles or volume and so on. Now here what we could tell is this term here can be written as N naught by V, where N naught is the number of particles in the zeroth state. Okay. While the first term is actually talking about what are the things in the excited state. And what has been seen is that now if your Z tends to 1, okay, what happens? This term becomes significantly large, right? So that means when Z tends to 1, there are more number of particles coming and getting accumulated at the zero state. And that is the phenomenon of Bose-Einstein condensation, which you also get from here. Okay. Now, from here, what we did see is that this integration can be, so once you write an expression for the pressure, suppose this is the expression that you get, and this is the expression for the number of particles. So here you get an integration which is defined like this. Excuse me. You get an expression for integration. So you get now this can be written in terms of this Bose-Einstein function, which is given by this integral here, right? So, and this is nothing but a series of Z. Okay. Explicitly, that's how the series looks like. So basically now you can actually put in like this, replace the expression for this integral in terms of the Bose-Einstein function, okay, by this relations, where lambda is your mean thermal wavelength. And similarly, you can write an expression for the internal energy of the system as well, okay, and this is how and this is how it would look like. Basically, once you, so this is a very general expression that we had got during when we started solving for the grand canonical ensemble, right? This comes from the ensemble theory, and now you substitute the expressions here to write it in terms of the Bose-Einstein function. So from here also you can try to relate the average internal energy with the pressure, and it would give you an expression like this. Okay. Now, if you look at the number of particles again, you would get an expression like this, which now tells you that, so N minus N naught means N is the total number of particles, N naught is the number of particles in the zeroth state. So N minus N naught is nothing but NE, NE by V. Okay. So NE by V is given equal to this value. So this again is telling you now, what is G? G is a series of Z, right? So, and we know that Z has a limit of its own, right? Z varies from 0 to 1. So that means there's an upper limit to this value. And if there's an upper limit to this value, that means there's an upper limit to NE, which is the number of particles in the excited state. So you can define NE as this, basically replacing N minus N naught as NE, so the number of particles in the excited state. And here Z gets extremely close to unity. So if you consider Z between 0 to 1, that means the maximum value of Z is equal to 1. So that means the maximum value of G, the Bose-Einstein function, is given for Z equal to 1. And if you put in the value of Z equal to 1, what you get is an expression like this. So that means now you can directly use this expression to define a maximum value for the number of particles in the excited state. Okay. And so now if you have to substitute it here, so it tells you that now NE has to be less than equal to this value. So that sets the limit to how many particles can be there in the uh, excited state. Okay. So for if the total number of particles is less than this value, that means all the particles would be distributed over the excited states, and then Ne would be comparable to N. But if the number of particles are more than this value, then these extra particles would start getting accumulated at the ground state. Okay, so now you have two terms. One is this, another is this. Okay, so this is your number of particle in the maximum value. It has reached the maximum value, and this is given as Ne, which is the maximum number of particles in the, because now you have replaced the Bose-Einstein function by the zeta function. So that means this is the maximum value, number of particles in the excited state. And then whatever extra term you have goes to N naught, which is the number of particles in the zero state. Okay. And from there, you can define Z, which is given by this relation here. So this is how it looks like. Now, based on this, what you can say is for all practical purposes. So here, whenever you are having this condition where Z is N is greater than Ne, your Z tends towards 1. Okay, and that's the condition of Bose-Einstein condensation. Now, this phenomena, as we discussed, is familiar to the very idea of a vapor condensing into the liquid state, but with certain differences. So this Bose-Einstein condensation is a purely quantum phenomena. Okay, and it happens in the momentum space, not in the coordinate space. Okay, so if you have to define a condition for the onset of Bose-Einstein condensation, it is given by this relation here. So whenever the number of particles exceeds this value, you get Bose-Einstein condensation. So from here, you can actually define a critical temperature given by this relation here. So we saw that for a ideal Bose gas, when you're talking about free particles in 3 dimension, your critical temperature goes as N by V, which is like you can define it as number density to the power 2/3. Okay, so that's the typical relation. And we did solve certain questions which made use of the fact that this is the relation between the critical temperature and the number density. Okay, so that means now whenever you are at a temperature lower than the critical temperature, that's when you would get this condensed phase arising, right? So there you would have two phase, actually a combination of two things. So one is a normal phase where you have this Ne number of particles over the excited state, and then you have a condensed phase where you have N naught number of particles accumulated in the ground state. Okay, so that's what happens when you go below the critical temperature. Okay, so this is something which we had discussed previously. And from here, you can actually try to plot how Ne and N naught varies with temperature. So you can see at, as you go to much lower temperature, like T tending to 0, you see that all particles would gradually come and get accumulated at the 0 state. And that's the condensation. Okay. And similarly, for values lower than Tc, Z becomes 1. So whenever you're talking about, temperature lower than Tc, you can always replace the Bose-Einstein function by the zeta function, because you can put Z equal to 1. Okay. So now this is your expression for pressure, okay, in terms of the Bose-Einstein function. So you can say that for T less than Tc, you can replace the Bose-Einstein function by the zeta function, and that gives you, so here you can see you have a lambda q, which tells you like lambda has a temperature dependence, right? It's the mean thermal wavelength. And then you again have another temperature term here, which tells you that now pressure goes as T to the power 5/2, and it's independent of, the density. So you can actually try to rewrite this expression explicitly, and you would see that this is an important relation. It tells you that pressure for temperatures lower than the critical temperature, pressure goes as Tc to the power 5/2. Okay, so these kind of relations can directly be used for different problem solving and questions, but you cannot keep on learning them. It's better to have the basics clear and try to solve it for yourself as based on whatever questions. Okay, some things will naturally be in your mind, but don't try to learn all of this. Okay, so remember how you are getting to this expression. So there can be very direct, numericals, which tells you that at some temperature below the critical temperature, the pressure is given, and you have to find the temperature. So the pressure is given and the Tc value is given, and now you change the TC value to some extent. So what is the change in the pressure? So all these kind of questions can come. For T greater than TC, there the Bose-Einstein function remains as Bose-Einstein function. Okay. So now you can basically, you have to replace this term here. Okay, so P equal to KT by lambda cubed into G5 by 2Z. So this G5 by 2Z by lambda cube can again be written in terms of another um, another Bose-Einstein function. So then you can write it by this relation, as you can see here. Okay, because G3 by 2 is nothing but lambda cube by V. So from here you can get a relation. Okay, so V is nothing but N by V. Okay, V is V by N. Okay, so this is how you can define a relation between the different Bose-Einstein functions, which is again function of the fugacity and the number intensity and temperature and the pressure. Okay, this is for T greater than Tc, this is for T less than Tc. Similarly, you can write an expression for the internal energy. Again, based on whether you are lower than the critical temperature or higher than the critical temperature, you can replace. So when you are lower, you can always replace the Bose-Einstein function by the zeta function. So that would give you a definite value. Okay, because there you are putting Z as 1. Okay, so this is nothing but a series of Z, and then you put Z equal to 1. So that means you now have a value for this series. Okay, so that gives you a net value of energy or net value of the specific heat and so on. And what we did see is that for T less than Tc, you can see that Cv is actually C by Nk equal is close to 1.9, which shows that it's larger than the classical value. Okay. For T greater than Tc, you can again start with this expression. And from here, you can use this relation, which is a well-known relation for derivatives involving the Bose-Einstein function. So you can use this relation to define this quantity and basically now find a relation that gives you explicitly Cv in terms of the different Bose-Einstein functions. Okay, so if you want to plot Cv versus T, you would see that the value at T equal to Tc is larger than what is expected classically, but then at lower temperatures, it goes as T to the power 3 by 2. Well at higher temperatures, it gradually tends towards the classical value. Okay, so till now we have been talking about free particles. Okay, so free particles in 3 dimensions. In 2 dimensions, only the the integration over the phase space volume would change, and then so the density of states would change. So that means here when you have this terms 5 by 2, 3 by 2, all these terms will be a function of the dimensions of the system that you're talking about. So all these terms would change based on whatever dimensions you are in or whatever dispersion relations you are in, but otherwise the process remains the same. Now we can slightly move to another system, which again involves bosons. Okay, but now it's harmonically trapped Bose gas. So it's trapped in suppose it's trapped in a 3-dimensional harmonic trap. What do we get out of it? Okay. So for free particle, we know that the density of state goes as epsilon to the power half, but that's not the case for harmonically trapped Bose gas, right? Because now you have a potential and it's a 3-dimensional potential. So now you have like half m omega x square, half m omega y square, half m omega z square, z square. So you have all these 3 terms. And then you have the kinetic term, which comes from p square by 2m. So for this system, because now you're talking about, so you're talking about quantum, indistinguishable quantum particles. So here you know that the energy levels are discrete. So you can actually, this is typically well known for particles in the harmonic potential. So now you can define the energy states as nx plus ny plus nz plus 2 by 2 h cut omega. So this is your 0-point energy. And these, based on whatever values of nx, ny, nz you choose, you would get different energy levels. So for our question, we can consider omega x, omega y, omega z to be equal to some value omega. Okay. In different questions, like there was some question in the previous assignment as well, where there were different like different frequencies in different directions. Okay. So in that case, you have to write it explicitly as omega x, omega y, and omega z. You cannot just, take common and consider it as omega. So those things are there, but otherwise the basic idea still remains the same. So based on whether you have a, same, frequencies for all the three directions or not, you have to be careful about how you write these terms, right? So now you can write an expression for the energy levels, and this is how it would look like. So the question here is, we want to basically again write an expression for the density of states for such a system. Okay, we did solve for the density of states for a free particle, free boson, but now if you have a harmonically trapped Bose gas, how will the density of state look like? And from there, can we actually relate to different thermodynamic variables? Okay, how to do that? So the number of state that lies between 0 to epsilon. If you want to find the total number of states, how will we do that, right? So now because you have a three-dimensional, harmonic trap, so you can say that epsilon x, epsilon y, epsilon z, right? These are the energy. So you can say that epsilon x plus epsilon y plus epsilon z, the sum of this should go to epsilon, right? Which is the net energy that we are talking about. So from there, you can actually put limits. So now what you are doing is basically the same thing as before, but now you have an integration over the three dimensions, the energies in the three dimensions. You are normalizing it by this value here. So here you have omega x, omega y, omega z. If all of them are equal and considered to be omega naught, you can write it simply like this. And then for each of these integrals, you can see that so for the first, basically you have a condition which is given as this should be equal to epsilon, right? So now if you want to put a limit to the value of Ez, you would say that Ez varies from 0 to epsilon minus Ex plus Ey, right? So that's what you have done here, 0 to epsilon minus Ex plus Ey. Similarly, now how much does Ey vary? So once you have done an integration over Ez, now there are two options, right? So now you say that your epsilon y varies between 0 to epsilon minus Ex. Okay. And then Ex can take all possible values from 0 to epsilon. So that's how you define this integral, right? Basically, you are looking at all the conditions which gives you the total energy as epsilon. Okay. So now you can do this integration explicitly, and when you do the integration, you would get an So when you do the integration, you would get an expression like this. So this is your expression for the number of states between 0 to epsilon. You have to find the density of state. That means you want to find the number of states between epsilon to epsilon plus d epsilon. So for that, you have to take a derivative of this term. Okay. So if you do a derivative, that means you have to find this term here. Okay. Okay. Right. So from here, you can write d epsilon as dg by d epsilon. Because basically, you're taking a derivative of the total number of states in terms of epsilon. And this is your expression. So you can see that for an harmonically trapped Bose gas, your Ge, which is the density of state, goes as epsilon square, which is like square of energy. Okay. Initially, for a free particle in three dimension, we had G going as epsilon to the power half. Here it goes as epsilon square. Okay. So that means based on the dispersion relation or based on the energy levels or based on the dimensions, all of this does affect the density of states. Okay. So now you can also, so if you want to now write an expression for ln q, we know that in terms of summation, this is how it looks like. But if you consider the volume is large enough so that the different energy levels are not that far off, so in that case, you can actually replace this with an integration. And when you go from summation to integration, basically you are doing an integration over G epsilon, okay, G epsilon dE. So that means any quantity when you're writing going from a summation of over the different distribution sets to an integration, then basically see this term is still here, but then you are doing an integration of that term multiplied by GE dE, right? That's the basic idea of going towards the continuum direction. Okay. So that means now you can actually try to define an expression for the number of particles. So you can write n as summation over n. This is nothing but your mean occupation number. Okay. So here you have the vivacity and then e to the power beta e minus 1. So now if you want to go from summation to integration, it's nothing but an integration using the density of states. So you do an integration of the same mean occupation number, but now you're using the density of states GEDE, right? So here, if once you know the expression for your density of states, just the one that we had derived previously, you can put it in here, okay, and then do an integration. So here you can consider beta epsilon as x and then substitute and you would get an integration like this. Now, why it is important is you can see this has a form similar to the Bose-Einstein functions that we are talking. So that means now if you know the definition of the Bose-Einstein functions, this is how the definitions are related. So now you can actually rewrite this integral in terms of a Bose-Einstein function. Okay. So that gives you n as this relation here. Okay. Remember, this is for a three-dimensional harmonic trap. Okay. For a different dimension, this expression would slightly change. Now, the maximum value of n. What is the maximum value of n? The maximum value of n would be when you put z equal to 1, right? And that's nothing but zeta 1, zeta z, basically. So, G3 of z, the maximum value of G3 of z is nothing but zeta 3, right? Basically, putting z equal to 1. So, if you do that, this gives you the maximum value of number of particles that can be there in the excited state. So from here, you can now actually define a critical value of n beyond which the condensation starts, and that's given by this relation here. So from here, you can actually replace T with TC, and you can find a relation between T with TC, which is like the critical temperature and the number density or the number of particles. Okay. So now for T greater than TC, what would happen? That means you are above the critical temperature. So there the NE is comparable to N, and there you cannot replace Z by 1, right? Z is not equal to 1 there, it is lower. So that means you again have this expression for N. So you have this expression for N. Whenever you're below TC, you can put Z as 1. Okay, so you can replace the Bose-Einstein function by the zeta function. But above TC, you cannot do that. Okay. So for T less than TC, N is greater than NE. And there you see that NE by N goes as T by TC whole cube. So that means you now see that initial, so this is TQ, right? So if I go back to the free particle in 3 dimension, what did we see? We saw that it goes as T to the power 5 by 2, right? So it all depends on, so this is pressure going as T to the power 5 by 2, right? And here, what do we see? Here, or if I have to actually, so pressure goes as T to the power 5 by 2. So from here, you can find a relation between the expression for, so you have a relation between TC and the number of particles, and it goes as 2/3, right? So this is for a free particle in 3 dimension. But then if you go to a harmonically trapped Bose gas in 3 dimension, then you are seeing that So here you can see that NE by N goes as T by Tc whole cube. Okay, so it's a different exponent. So all these exponents or the, mm, G nu, the nu of the Bose-Einstein function. Okay, so all these depend on the dimensions or the dispersion relations, the type of particles that we are dealing with. So for T greater than Tc, you have this relation. For T less than Tc, you have this relation. Okay. Again, for T greater than Tc, N0 is 0. Okay, because it's at T greater than Tc, everything is in the excited state. For T less than Tc, N naught is given as 1 minus T by Tc whole cube. Okay, because this is how Ne goes. And like if you have to, once you normalize it. So now this dependence is nothing but coming from this dependence, right? Ne by N. So now whatever remains is basically N naught. So that's why N naught goes as 1 minus T by Tc whole cube. So if you again have to draw an expression for Ne by N and N naught by N, you would see a similar expression, right? But there's a difference. The difference is in how fast it is falling or how fast it is rising. So this slopes or this rates are different, okay? While the nature remains the same. So one can now also define an expression for the average energy, right? So if you want to define an expression for average energy, what do? So in case of summation, we know it's written as summation over N epsilon, which is like the mean occupation number for that particular energy level, multiplied by the energy level value, right? So that's what gives you the average. So now if you want to write it in the integral form, you write it like something like this, where you again have an integral involving GEDE, which is the density of states. Okay. And otherwise, so for each, like GED is basically the number of, states between epsilon to epsilon plus d epsilon, and then you multiply it by epsilon, which is like the energy level, energy value, and then you have a mean occupation number, which is coming in here, right? So that's how you go from summation to integration. So now you can explicitly try to solve for it because you know for the question at hand, which is about the harmonically trapped Bose gas, you know the expression for GE, right? You know how it goes. So you can actually write this, explicitly and try to solve for this integral. So again, you would get an integral like this. Okay, you do substitution of beta epsilon becoming equal to x, and then all these terms you would be getting, and this is an important point. So now you again get an integral like this, where you can again rewrite it in terms of another Bose-Einstein function. Okay, basically, whenever you are having an integral like this, try to compare with this form, the form of, so try to compare it with this form. Okay, this is very important. So for any such integral, you can actually replace the integral with this Bose-Einstein function and be careful about it. Okay. So now basically, if you replace this here, you would see that you would get G4 of Z. Okay. So from there, you can actually try to find a relation between the average energy, the temperature, and then also the Bose-Einstein function for nu equal to 4. Okay, so here you can see that U goes as T to the power 4, right? When we are writing this expression. So for T less than Tc, Z tends to 1. Okay, and that's the case where so Z tends to 1, meaning this again is replaced by zeta. So this becomes a constant quantity. So you can say U goes as T to the power 4. Okay. So from here, you can also try to write an expression for CV. Okay, and this is how it would look like. So basically, once you know the expression for energy, okay, you have to write, you can just take a derivative to write an expression for CV. Okay, and here other terms are all like constants. So you can actually take a derivative for, so this should be T. So you can do a derivative with respect to like temperature, and you see this is how it looks like. So CV goes as T cube. Okay, so this is a typical relation that you see. So this is for the case where T is less than Tc. That means where Bose-Einstein condensation is happening. Okay, while so at this point, if you put T equal to Tc, what would you get? You would get an X value which is given by this value here. Okay, so that means T less than Tc, energy goes as T to the power 4, Cv goes as Tq, and then you can actually try to find an expression for the Cv by Nkb at the critical temperature. Okay, and this is the value that you get. Okay, now here there is a catch. So now if you again, see here, you could do this. You could do this when z equal to 1. So you get all these things. Now if T is greater than Tc, so that means in that case, this is your general expression for U, right? So you cannot replace G by eta anymore. So this is your expression that you would be getting for N. This is the expression for energy. Okay, and that gives you a relation between U and the number of particles as well, and the temperature. Okay, so this is a relation that you get for T greater than Tc, where actually like condensation has not started, right? So here now, if you have to find specific heat, you actually have to know how to do derivatives of this Bose-Einstein functions with respect to temperature, right? That's essential. So you can say that for T greater than Tc, U by Nkb is given by this relation here, but suppose you want to find an expression for the specific heat. So that means you have to do a derivative. So if you explicitly do the derivation, this term is something constant that you like, not constant, but it can directly be written in terms of the Bose-Einstein function. So this is how it looks like. But then when you continue with the derivation, differentiation, what you get is these terms here, right? So in order to define the specific heat, you need to know how G4 or G3, how are they, in terms of temperature, and how do you do the differentiations. So this derivatives are essential in order to find an expression for Cv at T greater than Tc. Okay. So here you can use this relation that for any M, so M can be the dummy variable, like for this case M is 4, for this case M is 3. So for any dummy variable, dgm dt can be written as dgm by dz into dz by dt, right? And this is something we all, sorry. And this is something we already know. So dgm by dz has this relation with gm minus 1z. So that means now what you can do is you can actually rewrite this as 1 by z dz dt into gm minus 1. Okay. So what is this telling you? That means you can write G4 in terms of G3. Okay. And then you can take G3 common, do many things, right? So you can say that dg4 by dt is given by this relation here. Similarly, dg3 dt is given by this relation here. So now you're relating the different Bose-Einstein functions. Okay. So now this is your expression for N. See, you still have to explicitly find these quantities that we don't know. If we have found a relation, but we finally want to find this value, right? So that's why we know that at for T less than Tc, or T greater than Tc, N is given by this relation here. So now you can actually do a derivative with respect to temperature. You get a term like this. So ddt of G3z. And we know how dt of G3z can be related, right? So basically we are using this relation. Yeah. So now, so what is this telling you? So this is telling you that you have taken a derivative, right? So you start with the expression of N, and you keep this on the right hand side and take everything to the left hand side, and then do a derivative with respect to temperature. What will you get? You would get this term, right? So ddt of G3z is given by this relation here. So now you know the expression for T3 of z, right? You can write and compare. And from there, you can see that ddt of G3Z is nothing but minus 3 by T G3Z. So that means now you can actually use those relations here. So these two were the relations, right? This was the relation that you got from the this exam, this point, right? Now what you do is substitute the expression for ddt of G3Z here. So that will give you a relation of 1 by Z dz dt. Okay, this is happening at constant volume because you're relating it to CV. So basically 1 by Z dz dt is like this at constant volume. Okay, so now this is your expression that is known to you. So if this is known, you want to finally you want to find these expressions, right? ddt of G3 or G4. So how will you write it? So you will write it as ddt of Gz is given as, so here this term is like ddt of, you can see here G3 of Z. So basically you're rewriting it as ddt of G3 or G4 is nothing but 1 by Z dz dt, and then you would get a G3 here, right? So if you have to write for G4, so ddt of G4 is given as minus 3 by T into this relation, okay, which is coming from here. Basically, you are replacing 1 by Z dz dt here, and then you have a G3. So now basically you can again put these values here, okay? So explicitly put the value of ddt of G4. Similarly, you can solve for G3, ddt of G3, okay? And then take common, you would get an expression like this. So now you can directly write CV for T greater than TC. So this is what you are doing for T greater than TC. For T less than TC, you can always, first step is replace the Bose-Einstein function by the zeta function, because you can put Z equal to 1. Okay, but here you have to actually explicitly find expressions that gives you these kind of relations for this derivatives. You have to substitute it, and this is the expression that you would get. So now here, if you put, so this is for T greater than TC, right? So for T greater than TC, this is your expression for CV. Remember this part, okay? This part is coming from only this section, right? You also have this term here. So now the overall expression for CV will be given by this relation here that you can see, right? So from here, CV by NKB will be written by this relation here. So here, if you put, so this is for T greater than TC. Now, what happens when you write T equal to TC with this relation, right? So then at the high temperature limit, again, you can put GZ going to Z. Okay, so again, what happens is you get 12 minus 9, which is like 3. So you get back the classical result, CV equal to 3 and K. Okay, but at T equal to TC, what will you get? So you will put Z equal to 1. Okay, so you will replace all the Bose-Einstein functions by the zeta function. So this is what you would be getting. So this is your expression. This gives you an expression of the specific heat at T equal to TC when you are approaching from TC plus, which is like when you are approaching from a higher temperature. Now, why it is important is that when you started with T greater than TC and you tried to write an expression for CB at T equal to TC, this is what you get. So this is the value, this gives you the value of specific heat when you approach the critical point from a higher temperature. While in the last case, when we were talking about T less than TC, there for the expression of CV, the specific heat was given as something like this. So that means the expression for CV, when you are approaching the critical temperature from lower temperatures or from higher temperatures, they're not the same. These are discontinued, right? So this does not match with the previous expression of CV at T equal to TC when approached from TC minus. Okay. So that means there's a discontinuity in the specific heat. Okay. So this is at T equal to TC, approaching from TC plus, and then when approached from TC minus, yes, my pointer. So when CV is approached from TC minus, this is what you end up getting, right? So these two are not same. So that means now if you There's a discontinuity which is given as delta CV by NKB, and this is how it is defined. So that means if you want to write an expression for Z as a function of temperature, this is how it looks like. This is an expression for energy as a function of temperature. But now if you plot CV as a function of temperature, you see that there is a discontinuity. So when you approach from high temperature, this is the value that you get. But while you approach from low temperatures, you get a different value. Okay, so there is a discontinuity. Okay. So this is for a harmonically trapped ghost gas in a 3 dimension. Okay. So now based on whatever we have discussed so far, if we want to extend this to suppose a harmonically trapped ghost gas in a 2 dimension, how would you do that, right? So the process would remain the same. Only when we are talking about the density of states, when when we are doing the integration over the phase space volume, right? So there the expressions would change because you are talking about a different dimension of system. So here it says that construct the theory for n bosons in an isotropic. So isotropic means you would say that omega x. So if it is isotropic 2 dimensional trap, that means omega x is equal to omega y. You can take it as omega naught, right? If it is anisotropic, there would be different values. So now it says that you have to consider a theory for n bosons in a isotropic 2 dimensional trap, and this corresponds to a trap in which the energy level spacing due to excitations in the z direction is much smaller than the spacing in the other directions. Okay, so basically, in a way, the energy, if you look at how the energy levels are spaced in 3 dimension, it is too much. The spacing is too much more. It's much larger than what you have in the other directions like x and y direction. And that's why basically you remain in the xy plane. You do not go to the higher energy states in a different z value, right? So that makes it a 2 dimensional trap. So it says that find the density, determine the density of states of the system. And then we have to see whether a Bose-Einstein condensation can form with this trap or not. What is the expression for critical temperature as a function of trapping frequency and n? And how much larger must the frequency in the third direction be for the system to display 2 dimensional behavior? Okay. So the first point is we have to find the density of states. Okay. And then, so whenever there is a question whether Bose-Einstein condensation will happen or it will not happen, you have to understand that if Bose-Einstein condensation happens, then you have a well-defined expression for the critical temperature. If if NE diverges or if TC is not well defined, so then in those cases, Bose-Einstein condensation cannot happen, right? So you have to look for that condition, and then you have to find an expression for the critical temperature, okay? And then see where this 2 dimensional behavior is, under what conditions this will be happening. Okay. So now we have done for the 3 dimensional harmonic trap. Here, what will happen? So in that case, you had nx, ny, nz. Here, you will only have nx and ny, right? And then there'll be like half h cut omega, again a half h cut omega. So that makes it 1 h cut omega, right? So this is how the energy levels are defined. So now based on this, you have to do the integrations to find the density of states. And because this is something similar, which we have just discussed, I'll give you some time to think and try to solve. The same idea, but now you have it's in 2 dimension. So accordingly, the integrations would vary. The density of state expressions would vary. Okay, so you have to find that. I'll give you some time so that you can actually think about it and try to solve. So you can see, basically you have to do this integration, right? So number of states, first you have to find total number of states, which is like capital GE. And then from there, you have to go to the density of state, which gives you number of states between epsilon to epsilon plus 2 epsilon. Okay. First, you're trying to find total number of states between 0 to epsilon. So initially you had in the last case like epsilon x, epsilon y, epsilon z. Here you only have epsilon x and epsilon y, right? So the basic condition here is epsilon x plus epsilon y should be equal to epsilon, right? Now you want to find the total number of particles which lies between 0 to epsilon. So that gives you that you can say that epsilon ranges from epsilon y ranges from 0 to epsilon minus epsilon x, and then epsilon x can take any value from 0 to epsilon. Okay, so that's the integration that you have to do. Let's try to solve it out. So if you do this integration, you get a value like this, right? So this is your expression for GE, that is the total number of state between 0 to epsilon, right? Now from here, if you want to find the density of states, which is like number of states between epsilon to epsilon plus d epsilon, what do you have to do? Think about what we have done before in the last case, right? So if you know GE, like the capital GE, the total number of states, if you want to find so if you want to find the density of states, you basically have to do a derivative of capital G with respect to energy or epsilon, right? So this will give you the density of states. That is the number of states between epsilon to epsilon plus d epsilon. So once you have this expression, can you find GE? Okay. So try to solve for small GE, which is the density of states. See, the process is same as what we have done for the three-dimensional case, only the expressions are changing based on whatever dimension of the system we're doing. Okay. So here what we can see is that GE would be given as dGd epsilon. So this is the value. Okay, so it goes as it's proportional to energy, right? While in the last case for 3 dimensions, if I go back and just recall, when we solve for 3 dimension, the 3-dimension density of state went as epsilon square. Here you have the density of state going as epsilon, right? Right. So now if it is asked that can a Bose-Einstein condensation form in this trap? So you know the density of state. The question is, will condensation happen or not? So for this question, you have to see whether you have a well-defined expression for Ne, which is like the number of particles in the excited state, or basically if you have a well-defined expression for the critical temperature, right? So for this, you have to start by trying to find an expression for the total number of particles. Now, in terms of integration, we know that the total number of particles can be written as this integral here. So you have this density of state coming in here. This is nothing but the mean occupation number. You do an integration from 0 to infinity. Okay. Now here you know the expression for GE, so you can substitute it here and try to solve for this expression. Here you can take B epsilon as a new variable X and try to rewrite the expression. And what will you get? You will get an integration like this. And then you can relate it to the general expression for the Bose-Einstein function. And you would see that now again you can write capital N in terms of the Bose-Einstein function. Okay, so that means now you have a definite expression for the total number of particles, right? So from here you can say that for T less than Tc, if condensation happens, then there'll be a Tc, and for temperatures below Tc, Z will be equal to 1. So in that condition, you can define N or Ne, which is like the number of electrons in the number of particles in the excited state. And that would be given as this value here. So here you have replaced the Bose-Einstein function by the zeta function. So this value is given as q squared by 6. So now you have a well-defined expression for the number of particles in the excited state. And thereby you have a well-defined expression for Tc. You can write Tc in terms of N and frequency, right? So that means there is a well-defined expression of critical temperature as a function of frequency and N. Okay. And because you have a well-defined expression for the critical temperature, that's already telling you that there is a possibility of Bose-Einstein condensation if you go below this temperature. Okay. So and again, for T less than Tc, condensate will therefore form. And how will it relate to temperature and the number? This is how the relation will be. So you can see here Ne goes as Tc cube. Remember, for the three-dimensional case, you had a Tc square. There you had Tc cube. Here you have Tc square, right? So then based on what is the dimension of your system, this dependencies vary. Okay. Be careful about that. So now you know that Bose-Einstein condensation can happen. You know the expression for the critical temperature. You know the density of state. The last part of the question says that how much larger must the frequency in the third direction be for the system to display two-dimensional behavior? So what it means is, so you know at the critical, temperature, suppose, you know that the typical energies in the X and Y, like in the two-dimensional plane, would be of the order of kBTc, right? Now, for the particle to be in this two-dimensional trap, the energy difference or the energy level gaps in the three-dimension should be much larger than this value, right? Only then it would be confined in the two-dimensional trap. Otherwise, it would go to the other Z, energy levels, right? So that means for it to display two-dimensional behavior, the occupancy in the first excited Z stage must be negligible, which again tells you that H cut omega Z should be much, much greater than kBTc. Okay, so that gives you a relation that relates how the frequencies in the third direction or in the Z direction should be related to the frequencies and the number of particles that we are talking about in the other two dimensions. Okay, so that under this condition, it would behave like a two-dimensional, like particles in a two-dimensional trap. Okay, it would not go to the along with in the Z energy levels because it's energetically not favorable. It's too high. Okay, so that's the answer. Okay. Now we did solve for ideal Bose gas. We tried to solve for harmonically trapped Bose gas in 2-dimension or in 3-dimension, right? So now, if you want to define a general treatment for Bose gas, how will we write it? So you can say that consider a general case where the density of states is given as something like this. So it's a general expression, okay, where the dispersion, the dependence of the density of states with energy is given by epsilon to the power alpha minus 1. Okay, so in this condition, how do we get general expressions for critical temperature or number density and everything, right? So here you can see that if we go back and look at the expressions for the questions that we have already solved, we know for free non-relativistic gas in 3 dimension, this is how this term looks like, right? So there you had, if you remember, for free non-relativistic gas, you had this value alpha as 3/2 because there the density of state goes as half, epsilon to the power half, right? So that means from there you can get that alpha is equal to 3/2, and this is the expression that we get. Now again, for a 3D harmonic trap, we know that G goes as epsilon square. So that means there alpha is equal to 3. So this is the relation that we had tested. These are the questions from the questions that we have already solved. Okay. So now we want to find a general expression for C alpha. Okay. So how to do that? So basically you can again start with the point that you want to find an expression for the total number of particles n. Okay. And this is how it would be defined. So now you know a general expression for your density of states. So you can basically replace this with this expression here. Okay. So if you do that and then do an integration, you would get terms like this. So from here, you can actually get an expression for the number of particles. Okay. So here, if you go to very high temperature, you can actually, replace G alpha of Z by Z, and from there find an expression for fugacity Z, right? And this will be useful when you want to define, suppose, an expression for energy and so on. Okay, you can use this relation. For T less than Tc, we know that Z goes to 1. So there you can again replace the Bose-Einstein function by the zeta function. And this is the expression that you will be getting. Okay. These are all general. So now if you put in and try to compare it with the results that you have initially already solved for, you would see that this will hold. Okay. So there's a general expression for n. So from here you can write an expression for Pc alpha, which will, so basically when T is less than Tc, Z tends to 1. So now if you want to find the critical temperature, you can put Z equal to 1 and then T becomes Tc. So basically beta, which has the beta is nothing but 1 by kBt, right? So you can define beta C as 1 by kB into Tc, right? So from here, you can actually define the critical temperature Tc. So for any general dispersion relation, if you know the density of states, how the density of state goes, you can actually find the relation for the critical temperature from here. Okay. Similarly, now if you want to find an expression for the average energy, how will you do that? So you can write this integration. You know the expression for the density of state. You can substitute it here, and this is the relation that you'll be getting. So here you can say that you have G alpha, right? G alpha of Z, and G alpha is nothing but a series in Z, right? So you can say that explicitly you can write G alpha in terms of the series, and this is how it would look like. So here for T much greater than Tc, that is at higher temperatures, you would see that this can be, approximated to the value given as energy equal to alpha in kBt. And that is nothing but the classical limit. So here, if you put alpha equal to 3, you get the harmonically trapped Bose gas. If you put alpha equal to 3/2, you get the free particle in 3 dimensions. So these are all classical results. And that happens when you are at a much higher temperature. So this is consistent. Okay. So you can also write an expression for the specific heat. Okay. And then again, try to see how it deviates. So this tells you how it actually deviates from the classical result. Okay, at very large temperature, you get the classical limit back. Otherwise, these are the correction terms or the modified terms that come in. So in high temperature limit, it approaches towards the classical limit. But there's an important point. You see that you have a plus sign here. Okay, so let me first remove this. So you have a plus sign here. What is this telling you? This is telling you that when you go to much higher temperature, you go towards the classical limit. But for lower temperatures, okay, or when you are like suppose T equal to Tc, so there the specific heat values are actually larger than the classical value. And this is something which you have also seen before, right? When we had solved for the free particle, we saw that at t equal to Tc, the ratio for Cv by alpha and Kb, that was around 1.9, which is larger than 1.5, which is the classical limit. So that means as we go towards the higher temperature limit, it approaches the classical limit. That's true. But then it approaches from a value higher than the classical value. So that means if you plot Cv, okay, and as a function of temperature, suppose. So if this is your classical value, it approaches the classical value, but from a higher value of. So if you want to write an expression for Cv versus T, this is how it would be. It would approach the classical value from a larger value. Okay, because so at Tc or at lower values, it's larger than the classical limit. Okay. So now based on what we have discussed, we can try to solve another question, which says that now show for an ideal Bose gas, this is true. Okay. And hence also show that gamma, which is the ratio of Cp by Cv, is given by this relation here. Okay. How to do it? Maybe just think for a while. Think about the different relations which relate the Bose-Einstein functions. We did solve for certain and derive certain relations which relate one Bose-Einstein function with another, right? Those will be useful for this question. So here, okay, okay. So here for this question, if you look at the expression for, P by Kt, this is the general expression, right? We know for an ideal Bose gas, this is the expression that something we have already derived before. Okay, so you can write pressure in terms of the Bose-Einstein function. Now, here, that means you can actually relate pressure with temperature, right? So lambda, which is like the mean thermal wavelength, also has a temperature dependence. So together, you know that P goes as T to the power 5 by 2. This is something which we have derived, right? Now here, what you can do is you can differentiate this result with respect to temperature at constant pressure. What would happen? This term, this left-hand side would go to 0, and right-hand side, you would get terms like del Z, del T at constant pressure and all this, right? You are doing a differentiation with respect to temperature at constant pressure. So from here, you can get an expression for del Z del T at constant pressure. Okay. So this is what you get, right? Now here you can see you have to find an expression for this. You have almost reached the value, but there is this 3 by 2 here, G 3 by 2. Here you have G 5 by 2. So that means you need a relation that relates G 5 by 2 with G 3 by 2, right? Now we know that del Z of Gm is given as 1 by Z, Gm minus 1. Okay, so that solves the question, right? So now you can find the expression for, you can just write del Z of G 5 by 2 is 1 by Z, G 3 by 2. Right? So, and then you can substitute that here. So you would get the first expression. Okay, so that solves the first part of the question, right? That solves the first part of the question. Okay. Now the second part, which is to find the relation for gamma, which is the ratio of Cp by Cv. Okay. So that means you need to find these expressions. Okay. Del Z del T at constant pressure, del Z del T at constant volume. Now, del Z del T at constant pressure is something which you have already derived here, right? You need an expression for del Z del T at constant volume. Now, for this case, we can actually go back to what we have initially discussed, right? So if we go back, see here for the harmonically trapped ghost gas, initially when we were solving, we started with N, right? And then did all this, taking a derivative with respect to temperature on both sides, and then trying to find a relation which relates ddt of G3 with G2, right? We used all these relations. So here we found an expression for 1 by Z del Z del T, and that is at constant volume, right? So that means now if you use the same procedure, okay, this was for a harmonically trapped ghost gas. For the question at hand, you have to do the same procedure, but for a ideal ghost gas with free particles. Okay. So for a free particle, what would happen? This expression, so the process would be the same, right? But what would change is basically this will change. Again, this exponents would change, right? All these things would change. So you can start with the general expression for a three-dimensional, particle in a free Bose gas, ideal Bose gas, and from there try to find an expression for these terms. Okay, and that would give you an expression for 1 by Z dz dt and all of that. So from here you can find 1 by Z dz dt at constant volume. This is the procedure. Okay. So if I now go back to the question at hand, by the way, this general treatment for postgrad is very important, also for in competitive exams or in solving questions, because this gives you a general expression which holds for all different cases of different systems with different dimensions and different dispersion relations, everything. Okay, just solve it once and remember how to do the basic calculation. Okay. Okay, so now if we go back to the question at hand, this is what we have to find. So we know Cp is given by this relation here, right? This is the definition. From the definition of Cp and Cv, we can actually find the relation which tells us that gamma, which is the ratio of Cp by Cv, is given by this relation here. This is straightforward. But now you have to replace the expression for del Z del T at constant pressure and del Z del T at constant volume. Okay. So del Z del T at constant pressure is this, which is something which we just derived in the first part of this question. And from the method that we have already discussed for the harmonically trapped gas, you can use the same technique for this free ideal Bose gas, and you'll see that you can find an expression which gives you 1 by Z del Z del T at constant volume. Okay, so now once you have these two relations, you can actually try to find and just put the values to get the expression. Okay, so here again, when T is much greater than Tc, okay, which implies that Z is a much smaller than 1. Okay, so you get back the classical limit, which is like 5 by 3, right? While when T tends to Tc, which is where the quantum effects become dominant. There Z tends to 1. That means this is where the condensation happens. Okay. So here the function G half of Z actually diverges. Okay. As alpha for minus half. Okay. And this again takes you to the point that, so there's a limit to, or when you're talking about, 3-dimensional free Bose gas, we did discuss this point that, D by S should be greater than 1. Remember? This was the criteria that we had solved in the last class, which tells us that this is the condition which is required for, condensation to happen. So again, here, what you are seeing is for a free ideal Bose gas, G of half diverges as alpha to the power minus half. So that again tells you that when you are in one dimension, what happens? In one dimension, your density of state, GE for one dimension goes as, so this goes as epsilon to the power minus half, right? So this is again telling you that, for Bose ideal Bose gas, you have to have cannot have condensation in one dimensions. Okay. So this is again telling you the same point. Okay. Which again also comes up because then here it diverges. So G of half, if it diverges, then it's not well defined. So this again sets the limit or condition to the fact that you cannot have condensation in all cases. It depends on what dimensions of system that you're dealing with, and also depends on the dispersion relation or how energy is related to the momentum and all these steps. Okay. So yeah, I think that's it. There are any questions related to anything? Because there's sometimes I'll be there for some time in case. So, going in. Otherwise, this is how it is. I mean, we almost covered quantum statistics to a greater extent, where we have discussed about distinguishability and indistinguishability of particles. We talked about, the different, so classical, distinguishable particle, and indistinguishable particle. There you have particles described by symmetric wave function, then particles described by antisymmetric wave function, the two main branches of Fermi-Dirac distribution and Bose-Einstein distribution. And from there, seeing how these different kinds of particles get distributed into different energy levels, how that comes up in the, macroscopic variables, okay, how they get reflected in the macroscopic variables, and try to solve for the, various phenomena that we see. So the Bose-Einstein condensation by itself is very interesting. Okay. So we did cover all of that. Now you can just, these are very standard questions. So sometimes in exams or in, competitive exams or even in assignments, you would get questions directly from this relations, or, just asking questions like, how does, for a system like this, how does the critical temperature vary when you change the density from this point to that point? Okay, this value to that value. Or if you are in a, suppose you're talking about photons in a 2-dimension or 1-dimension, is Bose-Einstein condensation possible or is it not possible, right? So all this kind of questions can come up, which is something which we have already covered. So if you go through the general results that we have found, there's a general technique, right? We know that there's a general expression that relates the Q potential or the grand canonical partition function with the fugacity or the mean occupation number. And from there, you can always go from summation to integration. Okay. Based on whatever particle you're talking about, you can choose the value of A accordingly. We know how to go from, based on the dispersion relations between momentum and energy, you can go from momentum space to the energy space, and that would give you the density of states. Now, once you have the density of states and you know the basic form in summation, you can go to the integration form and you can try to solve for an average energy or total number of particles, and from there try to define when suppose the expression for critical temperature and all of that. So that the technique is same based on different systems. The exponents and the values would differ. Be careful and and just practice a little bit about how you define the relations between the different Bose-Einstein functions. What is the general form of the Bose-Einstein function, right? What's the integral form and what's the series format? That's also useful because the series format also explicitly tells you how it deviates from the classical limit. Okay, so that's also an interesting point. Yeah, I think there's no other doubt. Yes, for a couple of minutes. I mean, all the results can be actually derived from this point. If so, so yes, set. There are no further doubts. Let's call it a day. Thank you.